This lecture is brought to you by CNCB Academy of Science and Technology. Visit us at cncbacademy.com.
Welcome back. Today's lecture is on classical mechanics. So we are continuing with classical mechanics, and this is the part 4 of the lecture. And I am Devasis Sanjan from the Department of Physics. We'll continue. So we'll do the first problem of today. So the problem is, an object is dropped on a cushion from a height of 10 meters. On being hit, the cushion is depressed by a height of 0.1 meters. Assuming that the cushion provides a constant resistive force, the acceleration of the object after hitting the cushion in terms of g is 100 g. G is the acceleration to gravity. So you have to prove it, right? So an object is falling, it falls on a cushion, and after that the cushion gets depressed by so much meters. So what is the deceleration what is the deceleration due to the cushion? And you have to show that it is 100 g. So I will do this problem. This is straightforward. So first it falls through 10 meters, and then through the cushion it falls through 0.1 meters, and so you have to find out the retardation. And you have to show it is 100 g. So this is up to you. You solve it. We go to the next problem. This problem is a turntable is rotating with a constant angular velocity omega naught. So in a rotating frame fixed to the turntable, the particle moves radially outwards with a constant speed v0. The acceleration of the particle in the r theta plane, as seen from an inertial frame whose origin coincides with that of rotating frame, is this. So you have to show this minus r omega naught square r plus 2 omega naught v naught theta cap. So r cap and theta cap have the usual notation. R cap is a unit vector in the direction of r, the radius vector, and theta cap is the unit vector in the direction where theta changes. And r cap is the unit vector in the direction where r changes. So what we have to find out, so here is a turntable that is rotating, and in the rotating turntable what we see is the constant speed v0 along the radius, radially outwards, which is moving with the constant speed v0. So this is a rotating frame, non-inertial frame. Now so if we are in an inertial frame, if someone in an inertial frame, then what is the acceleration the person sees? And you have to do, this is the acceleration. So what is how to do it? So this is the standard expression. So this is the acceleration d2r vector dt square in the inertial frame. I stands for inertial. And this is the acceleration in the moving frame or rotating frame. Here it is rotating. So what is the relation between them? The relation between them is given by this expression. So d2r dt square I is equal to d2r dt square m. M is moving, so everything is here with respect to m here on the right hand side. D omega dt with respect to, this is the change in angular frequency with time. Here there is none, so this term will be 0. And then will be there. So then it will be omega cross dr dt. Okay. So this dr dt is the velocity as measured in the moving frame plus omega cross r. Now what is r vector? So r vector, everything is on the right hand side in the moving frame. So in the moving frame, r vector is r into r cap. And what is dr dt? Dr dt in the moving frame is v0 r cap. That is what is given here. Moving radially outwards with a constant v0. So v0 r cap. And what is the angular frequency or angular, which is omega 0 k cap? That is, it is normal to the r theta plane. Here polar coordinates are being used. That's it. Now you have to find left hand side. Okay. So you have to find out this one. So you have to find out how does it look like. So here there will be two terms. So here it is moving at a constant speed v0. So of course here this part will be 0 in the in the moving frame v2, this acceleration is 0. But in the inertial frame this acceleration will not be 0, it will be like this. So there will be contribution from this term and this term. So dr dt is v0 r cap. So what is omega cross r cap? Right? Think omega is in the z direction, omega cross r cap. So that will be, if you think correctly, that will give us a direction in theta cap. Right? This omega and v dr dt, they are perpendicular to each other, but this is a vector quantity. So what will be the direction of the vector? Right? This should be in theta cap. Here also omega cross r cap. So omega cross r cap. So what is omega cross r cap? We know. So this is again omega and r are perpendicular to each other. So omega cross r cap will be theta cap. But again, whatever you are getting here, then if you do a cross product, this omega and theta cap, omega vector and theta cap vector also perpendicular to each other. But what is the direction? Think about it. Omega and theta cap, if you cross product, what will be the direction? It will be, direction will be given by r cap, but you have to take care of the sign also. Just think about it, you should get this result. And it's not difficult. Okay, so just do it. I have almost told everything. We go to the next problem. The next problem is, assume that the Earth revolves in a circular orbit around the Sun. Suppose the gravitational constant g varies slowly as a function of time. In particular, it decreases to half its initial value in the course of 1 million years. Then, during this time, show that the radius will increase 2 times. So, the gravitational constant g is changing slowly, and it changes to half its initial value. Then, what will be the radius? What will be the radius of the orbit in which Earth is rotating? It will increase 2 times. So you have to show that the radius will increase 2 times. Here we have to just think that this is my gravitational force, g mu by r square, and this gravitational force is actually the centripetal force. So the gravitational force is changing because g is changing. And as g is changing, the force is changing, but there is no moment, there is no torque acting on the system because force and distance are in the same direction. Hence, angular momentum will be conserved. So, m r square omega will be a conserved quantity. That's it. So, you can find out, you can eliminate omega from here, you can put it here, and you will get a relation between r and g. And you can see how r behaves with g. And from there you should be able to arrive at this result. Go to the next problem. The next problem is particle of mass m is on the plane. Particle of mass m is on the plane undergoes a circular motion with radius r0 and angular momentum L. And a small displacement epsilon, where epsilon is much less than r0, is applied. Its radial coordinate is found to oscillate about r0. show that the frequency of oscillation about R0 is 3m2g m1r0. What is the problem? So we will go here. So this is the problem. This is a table, horizontal table. So this is a particle of mass m, and here we have a particle of mass m2 that is hanging. So this is a hole, and the particle of mass m is because of this tension. The particle of mass m is oscillating about is rotating about this hole because of force m2. So what they are telling is that if this, so it's a circular orbit. So if this orbit is slightly disturbed, then what happens is that there is an oscillation of the radius. So that is what it means. That is what the problem. So the problem has asked you to find out the frequency of oscillation, and we have done this kind of problem before. Right? So this is so. So this, for that we have to go back to the classical mechanics part 1 lecture, and there we have done this problem. A particle moves in a circular orbit under the action of an attractive central force, Fr. Show that its orbit is stable if Fr is greater than minus r by 3 del f del r, Fr being the magnitude of the force. And in order to show it, we arrived at this final result, right? Delta is the deviation of the orbit, deviation of the radius of the orbit. So delta r, and delta r double dot is equal to minus dfr df dr delta minus 3f by r delta plus this. Obviously dl is 0. dl is the angular momentum. There will be no change in angular momentum, because radial variation, if you vary it along radius, there will be no torque and there will be no change in angular momentum. So only this part plays a role. So now in our case the force is mg, right? Our case the force is mg. So here, so that's what you have to prove. So if we have constant force here, so df dr is 0. So whatever contribution will come from this part, minus 3f by r. R is the equilibrium radius. Just put it here. This is not nothing different here. So m1 r double dot. This is the starting equation, right? And then I disturb everything. I move it, so really there is a disturbance of epsilon, and because there is a epsilon, there will be a disturbance in del theta also. So we have done this extensively in this one, classical mechanics part 1 lecture, and we arrived at this result. So now m1 delta double dot is equal to minus 3f by r, f is mg. So from there it should be, so this is the simple harmonic motion kind of differential equation. So from there we should be able to find out what is the frequency of oscillation. Okay. Go to the next problem. The point mass m is constant to move on the inner surface of a paraboloid of revolution. X square plus y square is equal to az, where a is a constant. When it spirals down the surface under the influence of gravity, convince yourself that the angular speed about the z-axis is proportional to z inverse. So what do we mean by this? So this is my parabola. So the particle is falling like this, is spiraling down. And the equation of a paraboloid of revolution is given. Sorry. The equation of paraboloid of revolution is given. So here one thing is important to note, that the angular speed about the z-axis will only change when there is a torque. What is the angular frequency about the z-axis if it is in this direction? Angular frequency about the z-axis, the angular frequency has the direction omega. This will be in this direction along the z-axis, and it can only change. The angular momentum can only change when there will be a torque in this direction, in the z direction. Then only the angular momentum will change, because the angular momentum also is in the z direction. The angular momentum for rotation about the z-axis will also be in the z direction. So only a torque around z direction can change the angular momentum. But here there is no torque in the z direction. The gravitational force is acting downwards, but the gravitational force is acting downwards vertically. But for that there will be no torque in the z direction. To have a torque in the z direction, there will be at least a component of force which is parallel to the xy plane. If only there is a component of force parallel to the xy plane, then there will be a torque in the z direction. Otherwise, there will be no torque. Hence, in this problem, angular momentum is conserved. Angular momentum along z direction is conserved. So that's it. So mr square theta dot is a constant. The theta dot is the angular velocity. And what is r square? R square is this distance. That's it. Now convince yourself that the angular speed about the z-axis is proportional to z inverse. Now go to the next problem. Two coupled oscillators in a potential Vxy is equal to, so this is the problem of coupled oscillators. So they are in a potential where Vxy is equal to half kx square plus 2x square plus half ky square. So two coupled oscillators in a potential Vxy, this is the potential, can be decoupled into two independent harmonic oscillators with coordinates x prime and y prime by means of an appropriate transformation. The transformation is given by x prime y prime. This is in matrix form, is equal to S x prime. Convince yourself that S is, so you said if this is the matrix, S is equal to 1 by root 2 minus 1 by root 2, 1 by root 2, 1 by root 2, then these two oscillators are decoupled. What do I mean? So in this variable x and y, so you can see these oscillators are coupled because there is a cross term. If there was no cross term, then you would have said that the oscillators are decoupled. But since there is a cross term, it means the oscillators are coupled. Now we can go to some other coordinates, okay, which can be a combination of x and y, such that in that coordinates, the potential energy becomes decoupled. So what do I mean by that? So what they are telling, if you do this kind of transformation, when S is this, then the oscillators will be decoupled in that coordinates. So what do I mean? So let's see. So this is this is S, so if this is S, then I can inverse it. I can write xy is equal to s inverse x prime y prime. So what you have to do? You have to find the inverse of this matrix. That's straightforward. Once you have found the inverse of this matrix, then you know x in terms of some x prime y prime, and you know y in terms of some x prime y prime. That's it. And if you substitute now, so now if you just go here and instead of x you put what you get here, okay, in terms of x prime y prime, and here also instead of x you write it in terms of x prime y prime. Y also you have to write in terms of x prime y prime, and here y square you write it in terms of x prime y prime. Then what do we get? Check yourself. I have not done the calculation explicitly. So you will get v. You get exactly this. V you will get half k minus 2 x prime square plus half k plus 2 y prime square. Here see it just got decoupled. There is no cross term. There is no x prime y prime term. X prime is separate, y prime is separate. So this is what they mean by decoupling. This is can be done by a suitable coordinate transformation. And once you have this, so if I go and write down the Lagrangian of this system, the Lagrangian of the system will be half m x dot square plus half m y dot square minus bxy. Now if I go to the new coordinates, then this Lagrangian will have this form. Check yourself. You already know x in terms of x prime y prime, so x dot can be found out very easily. Y dot can be found out very easily in terms of x prime and y prime. And if you do the calculation, if you put the value of x dot and y dot here, then what we get is half m x prime dot square plus half m y prime dot square minus v x prime y prime. And this whole system is now a system of two oscillators given by whose coordinates are given by x prime and y prime, and they are decoupled. There is no coupling between them. And from here you can easily find out what is the normal mode of vibration of this system. The normal mode is, this is the one mode will be root of k by 2 by n, and another vibration will be root of k plus 2 by n. Right? So this way we can say what are the normal. So for this oscillator potential, what is the normal mode of vibration? So what is the normal frequency of vibration? Okay, then what are the normal modes? Then so the normal modes, by decoupling we have found out the normal modes. So the normal modes have frequency root of k by 2 by n, and another will be root of k plus 2 by n. Do the calculations yourself. Here's another problem. A heavy particle of rest mass m, while moving along the positive z direction, decays into two identically like particles with rest mass m, flying off symmetrically with respect to the z-axis. Show that the momentum of any of the lighter particles along a direction perpendicular to the z-axis is half c m square minus 4m square. So this is the picture. So a heavy particle comes, okay, of mass capital M, rest mass, and it disintegrates into two lighter particles, each of mass small m, and this disintegration is symmetrical about this z-axis. So this disintegrates and goes in this direction, making an angle theta, and this goes in this direction, making an angle theta. So Pb is the momentum before V stands for before disintegration, and this is the momentum after disintegration. This is one particle, this is another particle. So what they have asked you is that the momentum of any one particle along this direction will be half c m square minus 4m square. How do we do it? So here we have used A. A is after fragmentation and B is before fragmentation. So what is E square? So we will use two relations. We will use one is the total energy relation. E square is equal to P square C square plus M square C4. This is the relation we will use. Only this relation. That's it. And conservation of momentum. Okay. So when you consider, okay, so this is the total energy before collision, and this is E. A is the energy of each particle after collision. So EB should be equal to twice E. And if you square it, you will get E square B is equal to 4 E square A. And PA is the momentum before collision, after collision of each particle, and PB is the momentum of the heavier particle. Okay? Now, just put this relation here and here, and you will get P square A in terms of P square B. Right? So we will get P square A in terms of P square B. Fine? Now we will use this relation. PB is equal to twice PA cos theta. And you can square it. So PB square is equal to 4P square A cos square theta. Now again, we have found out P square A in terms of P square B. So we can find out cos square theta in terms of P square B. Right? Do it, and then what we need to find out is this. PA sin theta is what? So we know. So we can square it. So we want to find out P square A sin square theta. So we know what is P square A in terms of P square B, and we know what is cos square theta in terms of P square B. So just plug in these values and you should be able to get this relation. Now check yourself what you get. Because doing is the most important thing. Okay, a frictionless horizontal circular table is spinning with angular velocity omega about the vertical axis through its center. If a ball of radius A is placed on it at a distance r from the center of the table, then its linear velocity is. So a circular table is rotating and a ball is placed somewhere on the table. So what will be the linear velocity of the ball? Now just think, there is no friction. Just at a distance r, this will be rotated to the center. Frictionless horizontal. This is important. Frictionless. So when you place a ball on something frictionless, what happens? So what is the force that is acting on this ball which has been placed on the table? There is only one force acting, that is the weight. Other than that, is there any other force that is acting? Okay, it is frictionless. So when you place something on a frictionless and that frictionless thing is moving, what happens? Will it participate in that movement? Think about it. Okay, if something frictionless table is moving and a ball is placed on the frictionless table, will it participate in the movement of the frictionless table, or will it stay where as it is? you have put the ball gently on the table. Now will the ball move or will the ball remain static? And the table is moving on its own. Think about it. The answer is very easy. Okay. Now we go to the next problem. The velocity dx of a particle moving in one dimension is given by dx is equal to v0 sine pi x by x naught. If the particle is initially at x by x naught is equal to epsilon, that is, when epsilon is much less than 1. Okay, so this is a very small quantity. Okay, the particle is such that it is at x such that x by epsilon naught is a very small quantity. We will show that as t tends to infinity, x tends to x naught. So the motion is such that as t tends to infinity, the particle will go towards x naught. This is what you have to prove here. Given is this relation, dx is equal to v0 sine pi x by x naught. So what we have to do? What is Vx? Vx is dx by dt. So dx by dt is v0 sine pi x by x naught. So now you integrate it. So you take sine pi x by x naught to the left hand side. So we will have dx some cosec pi x by x naught is equal to v0 dt. Integrate it. I will put in the integration result also. So if you integrate cosec dx, you get log tan x by 2 plus an integration constant. So if you do this integration, we now have to find out the constant. Now how do you find out the constant? To find out the constant, use this. So t is equal to 0, your x by x naught is epsilon. Use this condition to find c. Okay, find c, and then you will see you have to use you can use this relation. If theta is very small, then tan theta is approximately equal to theta. Somewhere you have to use this. If theta is very small, tan theta is approximately equal to theta. So that you have to use. And once you have used it, you will find the relation between x and tan. And then you see if t tends to infinity, how x behaves. You should see that x goes to x naught. So do the integration first, find the integration constant, and then for small theta use this relation, and then see the behavior of x versus t, and you will see that you will be able to convince yourself that this behavior is happening. As t tends to infinity, x goes to x naught. Okay. So we now go to another problem. A pendulum executes small oscillations between angles plus theta naught and minus theta naught. If tau theta d theta is the time spent between theta and theta plus d theta, then tau theta is best represented by which of the following plots. So there is a pendulum that is oscillating between plus theta 0 and minus theta 0, and tau theta d theta is the time spent between theta and theta plus d theta. Then what is, so tau theta is best represented by which of the, so 4 plots are given, 1, 2, 3, 4. Which one represents tau theta? Okay, tau as a function of theta. So this is tau, so vertical axis is tau and the horizontal axis theta. So which one is correct? For that we have to do a simple thing. So theta is equal to theta naught sine omega t. This is the oscillation, simple harmonic. Then we can immediately write omega naught is equal to sine inverse theta by theta naught. Or if you take the differential on both sides, we can write dt is equal to 1 by omega, then we will get some function of theta into d theta. This function of theta you calculate. Remember, this is sine inverse is there. And we know that I am even giving you the result. If y is equal to sine inverse x, if you take a differential, dy is equal to 1 by root 1 minus x squared dx. I have given the result also of differentiation of sine inverse x with x. Use this one here. But be careful, this sine inverse theta by theta now. It's very simple. So once you do this, you will get. So what you will get is an expression for. So this whole quantity is tau theta. Right. So dt is the time spent between theta and theta plus d theta, right? And that is given in terms of theta. On the left hand side, this is the time spent between theta and theta plus d theta, and on the right hand side, the expression is given in terms of theta. And this entire expression is tau theta. So find out what is the measure of tau theta and see which one is correct. Okay. Here we have minus theta naught, we have plus theta naught. Minus theta naught, plus theta naught. Minus theta naught, plus theta naught, minus theta naught, plus theta naught. Okay. We go to the next problem. A particle in one dimension executes oscillatory motion in potential dx is equal to A is some constant modulus x, where A is a constant of suitable dimension. The time period t of the oscillation is such that t is proportional to e to the power a. Okay. So the particle is oscillating in this potential, it's periodic oscillation, and the period of oscillation is such that t is proportional to e to the power a. Show that a is half. This is half. How do we show? There is a simple trick. Total energy is half mv square plus ax. So from here I can find out the dimension of m in terms of energy. So dimension of mass will be energy by velocity square, and dimension of A will be energy by length. Now the time period is equal to will be a combination of mass m to the power some exponent a to the power some exponent times energy to the power some exponent. The exponent can be positive or negative. So you have to find out what is the combination of these three, m, a and e, such that finally what we get is a unit of time, and that will be the time period of this system. Okay. So what we have to find out is to find out the suitable combination. So it's given, the dimensions are given. So we have to construct from m, a and energy a dimension of time. Right? So m to the power something, a to the power something, e to the power something, such that we get dimension of time. So do it. And it's not difficult. So here a particle of 1, so this is the mass of the particle, 1 GeV per c square, and its antiparticle both move with the same speed v. Produce a new particle x of mass 10 GeV per c square in a head-on collision. Show that the minimum v required for the process to complete is 0.9 ms. So this is the minimum velocity that is required to complete this process. So this is my lighter particles, Antiparticle will also have the same mass, same rest mass, and this is the mass of the particle that is created by the particle and the antiparticle. So this, and so what is the minimum V? For minimum V, the new particle X will have no momentum, no Planck energy. It will be only whatever energy it will have, it will be due to the rest mass. That we have to remember. So we will use two relations. So E square is equal to P square C square M square C4 and P is equal to gamma M. And this is the relativistic momentum expression. Now, so what we have to find out is the minimum V. So here, from here, so the E particle is the energy of each particle. Particle and antiparticle will have the same energy. So 2 times C will be the energy of the particle X, and the energy of the particle X is mx c square, because it has no momentum. Momentum is 0. You have to find out the minimum velocity required. Okay, so from here we can find out so from here we can, okay, and so from here we can find out the momentum of each particle. Okay, and once we find out the momentum each particle in terms of the rest mass of X, in terms of rest mass of X. So we will put it here, and then this we know, gamma, we know what is gamma in STR, and from here we can find out the velocity. But first we find out M, P from this expression, plug it in, and then this is given. So we have to find out the V from this expression. That's it. Go to the next problem. A particle is thrown with the speed v from the Earth's surface, attains a maximum height h. If v is half the escape velocity and r denotes the radius of the Earth, then show that h by r is equal to 1 by 3. So this is not difficult. So what is the escape velocity? Escape velocity is the minimum velocity that is required to leave the Earth. So that is kinetic energy plus gravitational energy should be 0, and that will give us the escape velocity. So find out escape velocity from here, and what we know for in this problem, the energy of the particle is half mv square, and v is half the escape velocity plus potential energy. This is the potential energy. This is just at the surface of the Earth, and at a height h above the surface, this will be the potential energy because its velocity is 0 there. That's it. So plug in the value of half of escape velocity from this expression, find out escape velocity from this expression, plug in the value here, and then find out h by r and see what to get. And now go to the last problem of today. The fulcrum of a single pendulum of mass m and length L oscillates vertically as zt is equal to a sin omega t. The pendulum moves in a vertical plane, and theta t denotes its angular position with respect to the z-axis. Show that the equation of motion of the pendulum is given by ms square 1 plus sin square theta double dot plus ml square sin theta cos theta dot square plus mgl sin theta g minus a omega square sin omega. This you have to prove. So what is the problem? The problem is this is some kind of support. The pendulum is attached here, and that support is oscillating. This is the oscillation. This is a known oscillation that is controlled. This is Zt is equal to A sin omega t. So this part is oscillating. While this part, while this is the length of the pendulum, this is the angle theta it makes with the vertical. Okay, so this is my, so this, and it is attached to this support, but the support, so this is a fulcrum, but this support is moving up and down periodically. So we have to find out the equation of motion of the pendulum. Okay. So there is only 1 degree of freedom here, theta. So first, how to write down the Lagrangian. Once we write down the Lagrangian, we can find out the equation of motion. So in a frame fixed to the fulcrum, in a frame this is what, if there is a frame that is fixed to it, then in that frame there is only the circular motion is happening. So the Lagrangian in the moving frame is kinetic energy minus potential energy, right? So this is the kinetic energy of the pendulum. So the L is fixed, right? L is fixed. So its kinetic energy is given by n r square theta dot square, where r square is actually L square. And this is the potential energy. So remember, this is at a height z. So this height, the height of the pendulum will be the height of this point of suspension minus this distance. So height of the point of suspension minus this distance will give you the height at which the pendulum is, that is this z minus L cos theta. So this z is being measured from some base, from some reference, and this is L cos theta. So the height of the pendulum from the base is z minus L cos theta. Okay. So this is the total energy with respect to a reference frame that is fixed to the fulcrum. But now in the lab frame, what do we see? In the lab frame, what we see is this. So this is, in the lab frame we see this point of suspension is also going up and down. So we define a coordinate z, capital Z, which is z minus L cos theta. Right? That is basically the height of the pendulum, from the base, isn't it? This is z minus L cos theta. So what is important here is that this z dot is important here, because now there will be a kinetic energy in this direction because of the oscillation of this point of suspension. So we have to find out z dot, and then we have to find out z dot square. So this is z dot is z dot it will be plus, so z dot plus sin theta theta dot, and then there will be bracket z dot plus L sin theta theta dot bracket. So it should be z dot plus L sin theta theta dot bracket. just a dot product, just taking the derivative. So that now the Lagrangian with respect to the gap frame or inertial frame is half mr square theta naught square plus half mz square, and so this is the kinetic energy now because we have kinetic energy in the z direction also, and this is the potential energy. Okay, and one thing is to remember that this z is now a function of time, because z is equal to a sine omega. So in the gap frame, z is equal to a sine omega. And so we have to solve the Lagrangian equation ddt del Li del theta minus theta dot ddt del Li del theta dot minus del Li del theta is equal to 0. Okay. So when you're doing, so first you will do del Li del theta dot. So it's given here. So wherever theta dot is there, you will differentiate. But then after that there is a total time derivative. So total time derivative will act on theta dot. It will also act on z. Okay. That we should remember. So z dot square. So you have to. So I am not writing what is the full form of z dot square. You have to write down z dot square also, and then take the total derivative, and then you should get this answer. Try it out yourself, it's not difficult, and that's it. So we'll stop here, and from next time onwards we'll do electrostatics and electrodynamics. So thank you.